say good morning first, and thanks for joining us today. We have another pretty good lineup of speakers for our webinar series. This is, again, a part of the North Central Region Climate Team. I'm Tyler Williams. I'm an Extension Educator for Cropping Systems for Nebraska Extension, and I'm located in Lincoln. We'll also have in the background is Hans Smits from Purdue, and he'll be kind of taking care of the logistics and making sure this all runs the way that it should. So today we have two speakers, Beth Hall with the Midwestern Regional Climate Center and Kenneth Hellevang from North Dakota State. So we'll first start with Beth today, and then we'll transition after about 25 to 30 minutes. Then we'll go on to Ken. So we'll probably hold questions till at least we switch speakers or at the end of the webinar, whatever kind of works out best. But so if you do have a question, but go ahead and you can go ahead and type that into the chat box at any time. Hans and I will try to keep an eye on that a little bit. I also want to mention, because I always forget, is that we'll have a couple evaluation questions at the end on the sidebar, so you can be looking for those too, because again, I'll always forget to mention it at the end. So we'll go ahead and get started. Beth Hall, again, is our first speaker. She's the director of the Midwest Regional Climate Center, which is located at the University of Illinois. She's been the director there since 2012, and as I was reading her bio a bit, she's been every place from the deserts to New England. So, you know, definitely served a bunch of roles there all across the U.S. And today she's going to share a little bit about the tools and services that the Midwest Regional Climate Center has, and specifically some of the tools that they have for agriculture. So, anyway, so I'm going to go ahead and quit rambling, and I'll go ahead and turn it over to Beth.
All right, thank you. You can hear me okay?
Yep, we hear you just great.
Thanks. So as Tyler said, with 25 minutes, I'm going to do a, a rapid review of a lot of the tools that the MRCC provides online. You can see from the map that's showing there are 6 regional climate centers. The Regional Climate Center program has been around for over 30 years, for us over 35 years. We get some support from NOAA to essentially take raw climate data, temperature, precipitation, humidity, and so forth, and make that usable information for the important issues within our region. So while we have access to data across the entire U.S., and so some of our tools are 50-state U.S. or 48-state U.S., we do try and make the applications and the tools be relevant to issues within our region. So I'm trying to advance, and nothing is happening. Oh, there we go. Okay. So I'm going to come back to this slide quite a bit through the presentation. This is the home screen of our website, and the web address is up there at the top, mrcc.illinois.edu. And essentially, I want to keep showing this because if you go to our website, this will be the fastest way to find the various tools that I'm going to talk about today. Off to the right, that's highlighted now with the red box, these are quick links that we have. And 4 of the 5 realms of climate tools can be found on these quick links. So while we have the navigation panel up at the top, that's the About Us, Data and Services, and so forth, most things you can just go to this quick link and get to the page of the suite of tools. The first one that I'm going to talk about is tools that were developed within the Useful to Usable project, or the U2U project. This was a 5-year funded project by USDA, the NIFA program, to come up with good decision support tools for the agricultural community. This is a highlight of, there were actually 5 tools that were developed within the U2U program. The 6th one that's in the bottom right, Probable Field Work Days, is a spreadsheet tool that was developed, I believe, outside of this program that users can download. But the other 5 have their own unique applications. There's the descriptions here, so I don't want to read them too much for you, but starting in the top left, the Ag Climate Viewer is an interesting way to go to a particular location across the domain for the U2U region and get graphs of temperature, precipitation, and corn and soybean yield so that users can look at how trends have been moving over the past 30 years. Below that is the climate patterns viewer, and that the thumbnail for that actually shows all the states that were involved in the UTU project. Right now, though, the project has officially ended, and both the High Plains Regional Climate Center and the Midwest Regional Climate Center are now hosts for those tools. And since we've adopted the tools, we really have the liberty to expand to different states or other regions or add additional features for these tools. So if any of you are exploring these tools and maybe your state's not represented or you'd like a certain feature, please reach out to the MRCC because we can look into modifying these for you. But the Climate Patterns Viewer is looking at teleconnection patterns of El Nino and the Arctic Oscillation. And depending upon what phase they're in, and the user can select, well, it's a positive phase or it's a negative phase, it will provide an indication for the crop reporting districts of what is that meant in terms of crop yield. Then moving below that is the irrigation investment tool. Here users can go in and they can modify different parameters to decide if installing an irrigation system would be worth it, would be profitable for their region, probably based on climatology, but historical corn yields and how much an irrigation investment would be pros and cons of doing that from a financial basis. Over to the right is the corn degree tool, and I'll show an example more of that next. But then the final one is the corn split N or nitrogen tool. And this one uses climate information to try and determine if it would be good to split the nitrogen application on the fields at different times throughout the year based on climatological parameters. So as I said, I'm going to, for the sake of time, just show you an example of this corn growing degree day tool. This is the most popular tool that stakeholders talked about and was promoted and people are using. Essentially, when you go to that tool, you start off with a map of the region. So again, you can see the states that were involved, and it's possible that even Kentucky could be included in this. And just with your mouse, you can click, you can zoom in, you can click wherever you want, and it will ultimately find the closest station, weather observation station, and it will then display this graph, and you can see the graph is showing a variety of information. But up at the top, even though there were defaults that started, the user can go in and change start dates, what a critical freeze temperature would be, if there's comparison years that they would like to have displayed. So if they knew that, say, 2012 was a particularly bad year, they can compare that with what's happening this year. And I believe there are forecast data that is included in this product. With the legend, we highlight here the date of silking and, and the black layer date, and then you can see how it even shows through the historical record the date of the first fall freeze, so that users can use this tool, play around with the different parameters, and get a better idea of growing degree day information. So again, I encourage you to go and check out the different tools. They were designed with a co-production method in mind, meaning that stakeholders were included throughout the process, but again, we're always interested in hearing more feedback on them. Now going back to the main homepage of the MRCC, the next project or suite of tools that I want to show comes out of our Vegetation Impact Program, or our VIP program. If you click on that link, you land on this page. We have our most popular project is the Frost Freeze Guidance Project, and I'll show some examples of that. And then you can see below that there's also a suite of tools that are vegetation related in terms of stress, chilling hours, and so forth. So let me start with the Frost Freeze Guidance Project. This started a couple years ago, and it's really been driven by the National Weather Service because each Weather Service office is responsible for their area. And when you are in the transition seasons of coming out of winter and then going into winter, that's when they coordinate whether or not they should send out freeze or frost advisories or warnings or anything like that. once we get into the heart of winter, the dormant season, if there's really not a lot of vegetation that would be at risk, they don't want to send these things out every day because the public would get numb to it. So they asked us to create a suite of tools that would help them better understand how much vegetation is out there that would be susceptible to a damaging freeze, so that they can coordinate from multiple offices so that they have consistency when issuing these freezes, and one office isn't issuing something that's contradictory to another office. So one of the products that we developed is a map that, and all these maps are updated daily, that shows the number of days since the most recent hard freeze. We do have accumulated growing degree days at their various base temperatures. A lot of these start accumulating since the most recent hard freeze, but we also have standard dates in there as well. Number of days within minimum temperature, with a minimum temperature that is greater, so warm enough for vegetation to think like it's coming out of dormancy. This is just 3 examples. We have a whole bunch of different maps on this frost freeze project. We even have hourly data that looks at the longest duration of a hard freeze or a basic freeze at 32 degrees. They are available on static maps similar to this, and also GIS maps, so the user can zoom in, zoom out, pan around, see what stations actually reported, and I believe even the data that goes into these maps can be downloaded in case people are interested in doing other analysis. But one of the key things with the Frost Freeze program is the communication aspect that the Weather Service office needs, but is also going to be important for state climatologists and extension specialists. The idea here is we want to know from anybody and everybody that, and this is now a 48-state project, whether there is vegetation that is susceptible, so that would be yes, whether there really isn't vegetation that would currently be susceptible to a freezing event, and the maybe. Well, there's some vegetables that's come out, not vegetables, but vegetation that has come out. It's not a full growing season has started, but we have a couple that if there was a freeze event. And so I really want to take the time here to reach out to any of the listeners, people in extension, master gardeners, just vegetation grower enthusiasts, to sign up. It's free. We don't share your information like that, but to go in there and participate in this program, because the Weather Service forecasters don't know the vegetation as well as the vegetation experts do, or even enthusiasts. So the more people that participate and actually state whether there is, isn't, or maybe a split, will make for more effective freeze alerts and advisories to be issued. Now, moving outside of the Frost Freeze program, but into just other tools that we offer within the Vegetation Impact Program, the VIP program. This is a map of stress degree day, where the map on the left shows an accumulated stress degree days, where that is defined as number of days where the temperature exceeded 86 degrees. Elwyn Taylor out of Iowa State University came up with a simplified algorithm for stress degree days, and they decided that for 86 this was appropriate for corn. So you can look at this map and see, well, how many stress degree days have accumulated in my area, to understand, well, how much stress has this crop been exposed to. And then the map on the right, if you're like me and have no idea if 300 is an important number or 500, it puts it into climatological perspective to show what is the departure from normal. So in much of the Midwest, this was polled on August 6th, you can see that we're right around normal in terms of stress degree days. But in other parts of the country, like the South, we're well below normal. It's been much cooler. And then in the West, it has been higher. Similar in layout, but a different tool is the Keach-Byram Drought Index. This is a drought index that is very popular within the wildfire community because it changes every day. There is an accumulated component to the Keach-Byram, also known as the KBDI, but the idea is, unlike the Palmer drought or the standardized precipitation index that has a memory that would be more like a month or several months, the KBDI's memory is really just a couple of days. So for those finer fuels, maybe grasses, it could be crops, a couple days without precipitation, but high temperatures could actually cause a rather rapid drought. So again, you have the actual KVDI value on the left, and these are updated daily, and then putting it into climatological perspective on the right to know if this is drier or wetter than normal. The next one is accumulated chilling hours. This is more relevant, I think, for the specialty crop growers, the orchard growers, where they have perennial plants that go into a dormant season and then they come out. The science behind this is that these types of plants that go dormant in the winter need to be exposed to so many hours within a critical range, and for this product we do a range between 35 Fahrenheit and 45 Fahrenheit, and we accumulate those hours over the dormant season with the idea that once we hit a sweet spot of the accumulated chilling hours, this will be indicative of the yield we can anticipate, the product yield for the next season, the growing season. So again, we have the actual accumulated, when we start the accumulation both October 1 in this case and September 1, depending on the part of the country that you think this should start accumulating, and then putting this into climatological perspective. Now moving on to another section of our website is the Midwest Climate Watch. This again has products that are updated daily. Most common are you default into the Maps and Image tabs, and you can see there's thumbnails for a quick look of what is out there, but for the most part it's going to be temperature. You can mouse over to see what the daily temperature was, max, minimum, average. We put it into climatological perspective. We have snowfall data, high-resolution precipitation data. We even provide the climate normals for all the parameters. And we have tools on here under the Maps and Images for things such as what is the date of the first 32-degree freeze and then the hard 28-degree freeze that is monitored for the current season, but users can also find what is the climatological, like what is the median date of the first freeze in the fall or the last freeze in the spring. However, we also have a tab here for the special topics, and if users click on that, we have 4 special topics here: agriculture, drought, Great Lakes, and winter. If you click on the agricultural button link, this is a screenshot of what that page looks like, and you can see that some of the tools that I've already shown you, so the UTU useful to usable tools are here. Over in the right, collapsed, you have this corn stress degree days, the chilling hour maps that I just showed, and the user can just expand or collapse any of these areas to get an idea of all the different tools that can be found. If I then click on the drought page or the drought link under special topics, same type of format, but if you want to see all the tools that we've hunted down that are relevant to drought, here's where you go. I'm going to look at the drought indices one because that one does offer some interesting stuff. If you expand that, you can see a variety of drought indices that link to the latest information of this. On the bottom row, second from the right, you see again these Keach-Byram drought index maps that I highlighted previously. We also have next to that on the left, evaporative stress index. That's a relatively new experimental product that's based on remote sensing and looking at the greenness of the vegetation. Next to that on the left, estimated precipitation needed to essentially get out of a drought once we're in a drought. And so on that page are a whole bunch of different tools that could be helpful for agricultural producers or planners to get an idea of what the climate conditions are. Next is our Climate, and that is our online data portal. So when users click on that, or before they even log in, it is again another registered site, but it's free to register. Here is a snapshot. This is actually a product guide that was for the Weather Service that highlighted in red all the tools that are available on Climate that's not available on their Weather Service online data portal. You probably don't need to know what's in red or black, but I'm just showing you a snapshot of all the different tools that are available on Climate. This is just page 1. Here's page 2, so you can see that we even offer hourly observed data products, state climate division products. We do maps and charts. So I'm going to show, let's see, you can go in, pick a station, and you can get very quick tabulated summaries. This is just an example of, for July, rank throughout all the years how much precipitation occurred at the Chicago Midway Airport site. And you can reverse. Do you want to go from low to high, high to low? Here's another tool that you can look at all the times when you had 5 or more days in a row with a max temperature greater than 95. Again, the user can play around with different parameters. It doesn't have to be just 5 days in a row. They can decide their run, their threshold, their parameter. But one product I do want to highlight here is our customizable maps. The users can find that once they log in under the maps of data. And looking at the different fields that the user can customize just in this main input window, starting from top going down, you can customize your dates. So if you want to look at a case study period of when conditions were a certain way, you can do that. Or if you just quickly want to do last month, this year. For location, we offer a variety of regions, not just the Midwest or not just the Regional Climate Center regions, but we have the Weather Service regions, the National Climate Assessment regions, fire regions, a variety of different regions. You can also just display the map by state. And then the Weather Service asked if we could zoom in further into their county warning areas. For the networks, this is another thing that's very unique, is most maps that you find at regional climate centers are relying on data from the cooperative network. And you can turn on and off if you want to include the COCO-RAWS precipitation data. If you're in Missouri, the Missouri Mesonet data is in there as well, so you can choose to have a map that includes all this data or just some of the networks. And I see that I'm getting close on time, but here's just an example of what that would look like when you're zoomed into a county warning area, and you can turn on or off the outline for that area. Also, there's wind roses under charts and graphs on Climate. This might be important for pesticide applications if you're worried about trying to apply the applications on a windy day or not. Again, as you go from top down, you can pick the dates that you want the wind rose displayed on. You can select particular hours, like if you know that you really want to apply the pesticide applications from 9 a.m. till whatever time, 7 in the evening or morning hours, you can do that. You can control things like units. My favorite part, though, to this is that last section where you can further control and say, I want to see a wind rose for when air temperature is greater than this temperature value threshold or in between these. So if you know you always want to do the spraying under certain climate conditions, you can set that, and then the output actually shows you what direction the winds are from and how often and at what speed. There's also under graphs and charts of climate that could be relevant for frost freeze. Considerations are probability graphs. This one seems a little complicated at first, but if you know your vegetation is susceptible at, say, 32 degrees Fahrenheit, then you'd keep your eye on that yellow line. And if you're trying to decide when in the spring you can actually start planting without risking a freeze, you look at the dates on the left and think, well, I'd love to be able to plant mid-April. So you find where mid-April is, you move across till you hit the yellow line, and then that tells you what the probability is of there still being a freeze after that date. And we have the similar product for fall freeze risk and then length of growing season. All right, there's one last thing I want to show you, and I'll go pretty quickly. It's not a fast link, but you can find it if you go under the Midwest Climate pull-down menu, and it is our Regional Mesonet program. This is where the MRCC has been working with a variety of mesonets, state mesonets across the region, and we are pulling data from the mesonets that is fairly rare, that you can't find elsewhere. So here's an example of the 4-inch soil temperature under bare ground, which is the upper right, or under sod. You can see how some states do both, some states don't do both. If you look in the legend, you can see how we try and augment the data from the mesonets with data from other sources, such as the cooperative network or the climate reference network. But another variable that we provide through the regional mesonet program is potential evapotranspiration. And in this case, we grab all the necessary parameters for the Penman-Monteith equation, and then we augment that with data from the RAWS networks, Remote Automated Weather Stations. So I like this one because there's not as many holes as there are in the previous ones. So with that, I'm just going to wrap up there, just have a little sloppy show here. But if anybody has any questions or feedback, I'm certainly willing to entertain them or send me an email. Thank you.
Okay, thanks, Beth. So we'll go ahead and get Ken switched over here, and we'll go ahead and get started with his presentation. We're doing great on time, so we'll have time for questions at the end, I believe. So again, Ken Hellevang is our next speaker today. He's a professor and an extension engineer from North Dakota State University, as I mentioned earlier. He focuses primarily on, grain storage, drying, and handling. And today he's going to share a little bit about how the weather impacts that, or some weather considerations for some of the grain storage that many of us deal with across our regions. I know, as we discussed earlier, some of the recent cool weather, people are already starting to get concerned about crop maturity, late harvest, and anytime you get into late harvest, you get into wet harvest typically, and if you're storing 2-year-old grain and you have to dry and store more grain, there's a lot of considerations, I think, coming up, and the weather is probably going to play a big role with that.
I noticed while we're waiting for Ken to bring that up that Janelle Peck asked a question, so I'm happy to answer that if that's okay.
Yep, go ahead.
So you noticed that Montana was missing from several of the maps, particularly the Mesonet maps. The Mesonet project originally started with just the Midwest states, and we've slowly been expanding out of that. So I'm happy to reach out to whoever runs the Montana Mesonet and see if they want to get involved. Maybe I can follow up with you separately about that. Thanks for asking the question.
Okay, thanks, Beth. Thanks for keeping track of that, like I said I was going to. Ken, I can now see your PowerPoint, and it looks like it's slowly ready to go.
Everything's in slow motion for some reason.
Well, hopefully it works out for you.
Okay, well, we'll go ahead and start. You should be seeing temperature affects grain storage. Let me move this out of here. And thanks for inviting me to do the presentation. Thought I'd just do a quick intro as to why that may be of particular interest right this year, and that is that based on the calls that I am receiving, and I field calls pretty much from across the region, everything through Nebraska, over east quite a ways. So the reports that I'm hearing are that we have a lot of grain in storage, and we got a lot of grain that may be held for a second year. So the storage management, I think, becomes very critical with the amount of storage that we have. I frequently make the statement that more grain goes out of condition because we're not controlling the temperature than for any other reason. And we'll touch on some of that, but also we'll look at temperature variations across the region and point out how come we sometimes will hear different recommendations for different parts of the region, that sometimes we do have to vary the numbers a little bit. So the two main problems that we typically see in grain storage is mold and insects. And I've got listed here a number of the parameters that affect both of those problems. And temperature is a key part of both of them. And so we'll be focusing on the temperature primarily today. but moisture certainly is a factor as well. From a storage standpoint, one of the things that I think is confusing at times is that the recommended storage moisture content does not always agree with the market moisture content. And I'm not sure how some of the market moisture contents got established. For corn, for example, we might be talking 15.5% moisture as a marketing point. That's what we use to define a bushel moisture content. But we really can't store the corn at that moisture content under warmer temperatures. So what I have shown here is a equilibrium moisture content, and that basically just says what moisture will the grain be at when it's in equilibrium with air at a specified temperature and relative humidity. So in essence, when is the air moisture and the grain moisture going to be similar? The reason that's important is that most of the molds will start growing somewhere in the ballpark of about 70% relative humidity. So if we're going to prevent mold growth, we need to keep the environment within that storage less than roughly that 70%. And you'll see different numbers used in the literature. Some will say 60, some will say 65. I tend to stay a little bit on the drier side so that we have a little margin of safety. So if we're looking at hard red spring wheat with air temperature at 70 degrees and 60% relative humidity, we'd be looking at a moisture content of that wheat coming to 13.3% moisture. That would be considered then the equilibrium moisture content. And so when you look at recommendations for long-term storage where we're going to be storing grain at temperatures that might be at 70 degrees or a little bit warmer, typically you'll hear 13 to 13.5% moisture is the recommendation. So if we take that fundamental principle then and apply it to the various types of grain that we're working with, corn, for example, has an equilibrium moisture content. And I'm going to get the pointer started here. Equilibrium moisture content of 12.8. So if we use that same idea of equilibrium moisture content, it would say we really need to look at 13% moisture as the safe storage moisture for corn. And that's typically lower than what a lot of times you will see listed. A lot of times they'll be showing 14% moisture, but really if we're thinking long-term storage under warmer temperatures, we probably should be thinking closer to that 13% moisture. Soybeans is another common type of crop across the region. EMC, or equilibrium moisture content, 10.2, and we really need to be thinking of about 11% moisture as the long-term storage moisture. So based on that, we can see that, as I indicated, not always do we have the market moisture agreeing with the storage moisture. For example, with soybeans, a lot of times we're marketing that at 13% moisture, but really if we're thinking of storing during summer temperatures or in the southern regions of the growing area, we probably need to be thinking more of 11% rather than 13%. Just to emphasize how important temperature is in storing grain, this shows the growth curve for a group of molds that are grouped together and called mesophiles. Being an engineer, I tend to just simplify that to say those are types of mold that like medium temperatures. It's the type of molds that we frequently will see in grain storage. The optimum temperature for growing that mold would be roughly here at the peak at about 80 degrees. And just look how drastically we change that growth curve just by cooling the grain from 80 degrees to 60 degrees. And we get down here to the minimum somewhere in the ballpark of about 45 degrees. So again, another reason for saying that we lose more grain because we're not controlling temperature than for any other reason. As we look at storage management, whether we're in North Dakota or Missouri or a southern region, the goal should always be to try to keep that grain as cool as we can to minimize the potential for that mold growth. I created this table many years ago based on research that had been done looking at allowable storage time. And the definition that was used at that point to determine allowable storage time was that there would be enough deterioration that it would occur that we would see a measurable loss in the quality of the grain such that number 1 corn would end up number 2 corn, for example. I averaged corn, wheat, barley, a variety of different types of grains together to label it just as cereal grains. And if we pick a certain moisture content, and I've been working with a farmer in Wisconsin that was trying to store 16% moisture corn through this summer. And the rule of thumb that I use, that every 10 degrees that we increase the temperature, we cut that allowable storage time in half. So at 50 degrees, we had roughly 230 days. 60 degrees, that dropped to about 120 days. 70 degrees, we were at about 70 days. 80 degrees, we were at about 40 days. So my recommendation to him was that we really can't store the 16% moisture corn through the summer because there's no way that we can keep that temperature low enough to successfully store through the summer. So he had to deliver that corn or dry the corn early summer, late spring, in order to have something that he could take to market. Moisture content also is important. Here, if we look at 70 degrees, 16%, we were at 70 days, dropping that moisture to 15%, increased it to 125 days. So this chart or table gives us a tool that we can use to make management decisions. If we're harvesting corn late fall, it's not drying in the field, we can look at this chart and get an idea of how long we can store that corn before we're going to have serious storage problems. Now this is based, as I indicated, on a determination of a loss that in quality that we could measure. It does not translate necessarily to germination, and we're seeing more and more malt barley growing across the region to feed a lot of these microbreweries. So let's look at a table for the malt barley where we're trying to maintain germination. Here, if we're looking at 80 degrees and 14% moisture barley, it says we have about 10 weeks of storage life before we will see a drop in germination below 90%. So if we're going to try to store seed or malt barley, we probably here, looking at this, probably want to be down at 12% moisture, or looking at making sure that we're keeping it below 70 degrees in order to store that malt barley without losing germination. And these tables or charts are on my website, and I'll show you that at the end of the presentation. Another reason why we're concerned about temperature is that the temperature variations as we go through the season will drive convection currents within the grain bin. As outside temperatures will cool, the grain near the bin wall cools, that air settles to the bottom of the bin, displacing this air in the middle and pushing that up to the top surface. We don't have time today to go through the long discussion that I normally do, but as that air comes up to the top, it can't hold as much moisture because it's coming in contact with a cool surface, kind of like a cool window in the wintertime, and we start getting condensation or high humidity conditions, and we'll frequently see storage problems, crusting taking place in the top of that bin. The way that we stop that is by cooling this grain as outdoor temperatures cool, and we'll look at specific recommendations in just a couple slides. We also will see convection currents taking place in the summertime or spring. Now the bin wall is being heated. That air will then rise, creating a suction, you might say, pulling the air into the grain mass. We have somewhat of a similar condition where we now have warm air coming in contact with cool grain. We'll typically see a moisture content increase here, maybe 4 feet below the top surface. This moisture migrant usually will only cause a moisture content increase of maybe 1/3 to 1/2 point of moisture. The fall and winter moisture migration can increase the moisture content by 5 to 10 percentage points. So the fall and winter moisture migration usually is something that we're very concerned about. The spring, summer moisture migration typically is not an issue, and if we were to warm this grain during this spring and summer by running an aeration fan, we would actually be increasing the moisture content of all of the grain. So we're normally not concerned about this, and the goal is to keep that grain cool. Well, if the goal is to keep it cool, we need to do it in some manner where we're moving outside air through the grain. Grain is an excellent heat sink, is an excellent insulator, and it'll stay warm into the cold winter months if we're not doing something to mechanically cool that grain mass. This is a visual I put together a few years back where I show here with a curved line the average monthly temperature for North Dakota, show different temperature bands and the recommendation of running fans periodically to cool that grain as outdoor temperatures cool. If we can get the temperature down below 70 degrees, insect reproduction is reduced. Below about 50 degrees, insects go into dormancy. And for those that are in the northern region where we can bring the temperature below freezing and hold it there for a period of weeks, we can actually kill the insects. So the recommendation is to cool the grain whenever we're looking at the grain being warmer than outdoor temperatures. And the rule of thumb is if there's about a 15-degree temperature difference between grain and average outdoor temperature, we run the fan to cool that grain mass down. Hold it cold over winter, and then in the spring we may want to run the fan to create a uniform environment within the storage, but we want to keep it cool as we go through the spring and summer as long as we can. And the target should be somewhere in that 35 to 40 degree temperature window. And that's going to be true whether we're in North Dakota or Kansas or some other southern region. The goal always is to try to keep that grain as cool as we can as we go through the summer. As we look at monthly average temperatures across the region, we see here on the left side North Dakota temperatures for January, April, July, and October. We have temperatures in January that allow us to bring the temperature down to the temperature that we want for winter storage. As we look at even the southern states, we have temperatures that allow us to bring it down to roughly that 30 degrees, even in the very southern part or across the region. As we look at going into spring, if our goal is to keep that temperature at roughly 35 to 40, waiting until April may be too late, because now we're looking at temperatures that may be above what we want. So this might be something that we want to think about as a management strategy for March or even earlier, depending on where we're at. And then as we look at summertime conditions, we have some very warm temperatures during the maximum temperature of the day, but we still have some cool nighttime conditions. And that's important as we start trying to keep the grain cool during the summer, and I'll show you that in just a moment. This is the formula that we use to estimate how long it takes to run the fan to cool a grain bin. And two things here. One is that the cooling time typically is only about 3 days, and we don't need large fans to do that. Even on this 42-foot diameter bin, 24-foot depth of barley, a 3-horsepower fan is plenty big to cool at within 3 days. And the cost is relatively inexpensive. I've got a lot of numbers here. I won't go through it, but just to emphasize that we can run even 12 cycles, aeration cycles during the year, and our cost would still be less than a penny a bushel for all of the benefits that we get. And so there just is, I don't know of a better return on investment. Now certainly the purchase cost of the fan isn't included here, but this is assuming 10-cent electricity. Even if we have more expensive electricity, it does not cost us a lot of money to properly manage this grain. So we want to cover the fans to prevent warming. This is one that I see done very little. Covering the fans keeps out prevents that spring up both due to wind into the fan and the effect. So this is a management strategy that we need to be thinking about. The other thing is that we need to take into consideration solar heating. Galvanized metal is a wonderful solar absorber, and when we look at the amount of solar energy hitting that bin as early as February, and certainly on the bin roof as we go through the summer, we may need to be running aeration fans or doing things to periodically cool that grain mass. The one that I think that we really need to be thinking about is ventilating this space in the bin roof. It may be as simple as having openings at the eave, openings near the peak so that it works just like the attic does in the house. And more we're seeing fans on thermostats operating to cool that headspace. Another option for summer storage is to have that grain cool on the bottom as the top warms up. Periodically, maybe a couple cool mornings, run the fan for just a few hours to utilize this cool grain to cool down that top surface again. My recommendation is that we need to monitor temperature and moisture and insects during the storage period every 2 weeks until the grain has been cooled, maybe every 2 to 4 weeks during the winter, and then every 2 weeks again at a minimum as we go through the spring and summer. One of the tools that we have are temperature cables or temperature sensors in these bins to help tell us what the grain temperature is throughout that grain mass. One thing to keep in mind, though, is that grain is a good insulator. And so if we're measuring the temperature at this point, it's not telling us what's happening over here, maybe 2-3 feet away from the sensor. But I am a strong supporter of using the temperature cables or sensors. Without them, we don't have any idea what's going on in that grain bin. But it is a tool to use in addition to our normal practices. There's a whole smorgasbord, you might say, of tools available, everything from manual readouts to ones that are linked to your computers and turn fans on and off. And I encourage people to consider these tools. The best way to find my material is just to do a search for NDSU grain drying and storage, and a lot of the tools that I have put together, a lot of the publications are there, and I encourage anyone that wants further information to look at that, or feel free to give me a call. So I've about used up my time and then some, but if there is time, I'd be happy to try to answer a question.
All right, thanks, Ken. Appreciate that. I didn't immediately see a question for you on there, but I do have probably a simple one for you. And so can people just assume that the grain going in is similar to the average outdoor temperature during harvest? Or is that a terrible assumption?
That may or may not be true. Again, we start thinking of the amount of solar energy that might be hitting the grain. If we're working with wheat, for example, or small grains, we might see the grain temperature considerably above outdoor temperatures. As we get into corn and soybeans, there's not as much solar energy, so we're probably going to be closer to the average outdoor temperature, but there is going to be a difference between the grain temperature and air temperature outdoors.
Okay, thanks. There was a question here for you. What's the most common mistake or missed opportunity you see among producers?
Well, I think the producers are getting better, but I think people know that they should run fans, so they just turn the fans on and let them run without understanding the management aspect. We waste a lot of money, I think, because we're running the fans more than is necessary initially in storage. The other one that I'm hearing frequently is that people are concerned that grain goes through some kind of a change at temperatures below freezing, and so they hesitate to run fans when it's a little bit cooler outside. We have extensive experience as well as research that shows that we can run fans and cool the grain below freezing, but there's really no benefit to go. The statement that I make is that 20 below is not better than 20 above. Once we get down to that temperature of 20 to 30 degrees, there's no benefit to cooling the grain below that. But probably the biggest one would be covering the fans. That the snow will blow into those open fans, into those ducts during the winter, and then we have lots of warming that occurs during the spring and summer if those fans are not covered. So probably the number one would be covering fans, followed by not managing the fans appropriately.
Okay, thanks. There was one more question in the chat box. This one was for Beth. So Beth, if you're still on, it's from Erica. Asked about the U2U tools, if they were still being updated on the MRCC site, or if MRCC has funding to maintain these tools in the future.
Yeah, hi. So when we, as part of the contracts that the RCCs would adopt, if you will, the tools that were created, with the assumption that the RCCs receive base contract funding from NOAA every year to essentially keep these products running. So it is through the contract funding that we will sustain the tools, and then any interest in having tools modified or expanded to other states or regions, if it's high enough priority, we can do that work within the funds of the contract, or we can always look for grant opportunities to provide the funding to do the modifications. But the contract itself will make sure that these tools continue to run and be sustained.
Again, thanks for Ken and Beth for joining in today. This will be recorded, or is recorded, and will hopefully eventually get put together, and we'll be able to send out a link for this as well if you have any interest in watching the recording, or if you know other people that might. So you can look for that coming up hopefully soon. So with that, again, thanks for joining in. Thanks, Ken and Beth, and this will go ahead and end our webinar.